Welcome to the Jack Westin MCAT podcast with your hosts, Michael Maleka
and Molly Hudash.
Hello, everyone, and welcome back to another episode of our Jack Westin MCAT podcasts with your hosts, Mike and Molly. Mike, super excited to be here with you today, especially to help support me through this episode.
Yes.
If you guys can hear it in my voice, I am recovering from COVID. So if I sound a little weird, that's why. But we simply couldn't wait to bring you some more action-packed value in this episode. So I'm glad that we're doing this.
Yeah, no, when we first got on the call, I was like, okay, like your voice isn't that bad, but it's not the Molly Hudash that I know, right? It's a little bit off, but hey, you sound fine. If you sneeze or cough, we'll all blame you, obviously. But no, we're just kidding. But
as you should.
As we should. But no, I'm just super happy that we can keep on doing this because again, like today, I think the episode today is really, really great. It's a really great addition to what we've been doing. Because last episode, we talked about the homeostasis, the equilibrium, which built off really, really well from the episode before, where we talked about the circulatory system, cardiovascular, lungs. So I think today's topic, right, really puts a lot of those things together and will get built in really well to even the next episode. Again, we just keep on teasing the next. And so what are we talking about today, Molly?
So today we're going to talk all about the kidneys and the functional unit of the kidney, which is the nephron. And you're right, this hits on homeostasis and equilibrium, cardiovascular and respiratory system. It even applies to our very first content-based episode, which was all about fluid dynamics.
Of course.
So I think this episode really does tie together everything that we've talked about. Because we're going to talk about pressure, we're going to talk about flow, we're going to talk about blood filtration, we'll talk about equilibria. So kind of a fun culmination of a lot of different topics today. So again, we're going to focus on our kidneys, kind of the internal chemists of the body, so to speak.
Right. Interesting way to think about them. I like that. Internal chemists.
Yeah. They basically are maintaining homeostasis on a organismal level. That's their job, right? So we're going to talk again about the kidneys today, and this material is very high yield, right?
Extremely.
Because not only can it show up in those standalone questions, right, or in the pseudo-discrete questions, as we like to say, basically a question that might be tied to a passage, but pretty much is just content, but could also really be tested in a lot of experimental passages and as an application of a lot of other topics that you may see in, chem phys or in biochem. So super excited. This topic will be everywhere.
Right. Like a lot of these crossover topics, I swear the MCAT loves choosing things that are cross-sectional, that love hitting on multiple topics. They start talking about the lungs, and they're like, oh, hey, here's the impact on the heart. Oh, here's the impact on the kidneys, as, in medicine there are. So whenever you have these topics that are so closely interrelated, right, the MCAT, that's great. What's the word I'm looking for? That's a great target for them to be like, if we want a passage, this is a great one to do because it can test so many things. There's a lot of options here. So that's why I think if you're listening to this and you haven't seen the last few episodes, highly recommend watching them because this is the kind of content where you want to be combining things together, not to be thinking about these organ systems in isolation or by themselves, right? Which is the goal that we want to be doing. Through this podcast, we're all about, being intentional, right? That's the word. If there's one word, it was all about being intentional, but also
catchphrase.
like learning, right? We're not just studying the kidney, we're learning how it integrates in the whole body because in the future as physicians, when you prescribe medications, when you're looking at symptoms, you have to realize how interconnected all these systems are. So yeah, definitely paying attention to this episode is going to be really, really critical for understanding, how our body regulates and how all these organ systems are connected. But I guess we'll start off with, let's start off with the functional unit of the kidney, which we've referred to before, which is the nephron. Molly, just a really quick overview. What are the different segments of the kidney?
Yeah, so I feel like it's important before we dive into the nitty-gritty with the nephron to just kind of set the stage here, right? We know we're talking about the kidneys, those little bean-shaped organs. You got one on the right, one on the left, retroperitoneal, not that you necessarily need to know.
That's a word.
On your back and outside of that normal abdominal cavity, right? Which is why if you have like a UTI that's spread to your kidneys, you might have back pain,
Mhm.
right? That's where they're located. The overall function is to filter the junk out of our blood.
Mhm.
And we talk about them as this whole bean-shaped organ, but kind of like a muscle is made up of a ton of tiny units, right, called sarcomeres that actually contract. The kidney is made up of a bunch of tiny units called the nephron that are ultimately contributing to blood filtration. Okay,
Mhm.
so we're going to talk about the different key components of the nephron, which again is a tiny, tiny, tiny unit of the kidney, but that does filter blood independently. Right, so
Mhm.
we'll talk first about the Bowman's capsule, which is going to be kind of this little cup surrounding capillaries, right?
Mhm.
Remember capillaries
From the
are
lungs, from the cardiovascular system,
yes,
right?
we
Mhm.
talked about the alveolar capillaries with respiratory system, and of course we mentioned them because they are blood vessels with circulation. Bowman's capsule is going to be surrounding those capillaries and then feeding into the proximal convoluted tubule, which is like a little maze. That's why it's
Mhm.
convoluted, right?
Mhm.
We go down deeper into the kidney and then back up in what's called the loop of Henle. Then we enter another little maze, this time called the distal convoluted tubule. Proximal, by the way, means like closer to
Mhm.
the origin, I guess you
Mhm.
could say, in anatomical language. Distal is further, so proximal first, then distal. And then we're going to leave through the collecting duct, which is going to feed into the ureters and out of the body, right, through
Right.
the urine. So
Right.
that's kind of the basic layout if we want
Right.
to try and start visualizing what we are experiencing on our little tour through the nephron. But I feel like we've really only hit on a tiny little piece of this puzzle with that because we need to
Right.
understand what we are going to see along each of these little stations on our roadmap,
Right. Each
right?
one has
So
its own special function that I think the MCAT loves to test on these functions. They're like,
yes,
what's the impact of, the proximal? What's the impact of the distal? So while it is important knowing the order, each one having its own function really critical. But before we can talk about each one's function, there's some terminology I think we should be familiar with before we start getting into nitty-gritty. And I think there's kind of
Mhm.
four really key terms to know that we'll be using them quite a bit in the different sections.
Yes.
So knowing these terms really, really important. The first one that we've already sort of talked about a little bit, which is filtration. When we
Hmm.
see the term filtration, that term means that we're moving from the blood into the nephron through the glomerulus, through the Bowman's capsule, because that's where that filtration is happening. I mean, we'll dive into it a lot more in a second, but like that's really where it's kind of like a sieve, right? Where it's like kind of like going through that and getting filtered through, not very selective. But when you see the term filtration, that's what you'd be thinking of, like where it's filtering from the blood into the nephron. Another key term to know is reabsorption. The idea of reabsorption, when you see this term, we need to be thinking reabsorbing from the nephron back into the blood. Right? A lot of times we get this flipped where we're like, oh, reabsorbing, blood into nephron. No, no, no. When we say we're reabsorbing, it's in the context of the body, right? Because we kind of say like the nephron's like kind of external. So we're reabsorbing it back into the body. So when we're saying
Yeah.
there's a kidney reabsorption from the nephron back into the blood.
As a note, just to because so many students are curious about this or confused by this, when we talk about absorption, we mean from the gut.
Hmm.
And we mean we are bringing it into the body for the first time. So reabsorption, it's
Hmm.
already been brought into our body through
Hmm.
our gut, right, in our small intestine. And then we are filtering it out and then we are
Reabs
reabsorbing. This is now the
back in.
second time. Yes.
Right, we're going to bring it. We like lost it. We're like, no, no, no. We actually want to take that back. So
Actually,
we're
yeah, come back. Yeah.
retaking that back. And there's one portion that's really, really big for that,
Yeah.
which we will talk about. Quite opposite to reabsorption, though, is this idea of secretion. Because a big idea with the nephron is that while a lot of things make it into the nephron through the glomerulus, secretion is this idea that there are other ways things can move from the blood into the nephron. So think of secretion as the exact opposite of reabsorption. If reabsorption is going from the nephron back into the blood, secretion is going from the blood into the nephron. But notice, it's not the same thing as filtration. Both of them are going in the same direction, but the mechanism is very different. Filtration, again, filtering through that glomerulus, whereas secretion could be in other parts of the nephron. So knowing these terms, reabsorption, back in, secretion, out. Final term, which again, we really don't want to mix up with secretion, is excretion. This
Hmm.
again, notice those words are similar, and you might be thinking, oh, they mean the same thing. They do not. Secretion is going from the blood into the nephron, right? Excretion is what actually leaves the body in the urine. So when something is excreted, that means it's leaving, the ureter and going into the urine. So it's leaving the body. So that's when something is excreted. Right? Very
Hmm.
different from secretion. The MCAT loves to kind of notice that little difference there and really likes to test that difference. So make sure that we have these terms straight especially when we're having this conversation about the different portions.
Yes.
Yeah. Yeah.
So now that we've kind of established what the different functions of our kidney are, and
Mhm.
those key terms that you're going to see all over the place in these passages, I feel like we're ready to put things together.
Mhm.
This segment is one of probably the highest yield of the episode, right?
Mhm.
It's going to be a little detailed, so buckle up,
Yeah.
right? But we want to go through the nephron again, and we want to make sure that we highlight what happens in every single stop along this pathway, right?
Mhm.
To get from the blood, our starting place, out through the urine, right? Okay, so let's start with the bloodstream, right? So we know, as we talked about, that we have a capillary, right? A capillary is when we have, a ton of blood flow coming through the arteries. They narrow into arterioles, and then
Mhm.
they enter capillaries, which are ultimately the thinnest, right? We have many components, including red blood cells, moving like one cell wide, single file line, very, very narrow. Um, these arterioles coming in to the glomerulus, which is a capillary, are bringing blood to be filtered into the nephron. That being said, the blood is contained within the capillaries. Okay, we
Mhm.
don't have just like, we don't have blood flowing directly into the glomerulus, or
Mhm.
sorry, directly into Bowman's capsule. What we
Mhm.
have is the blood flowing through what we call afferent arterioles, which means coming in. I always think of it alphabetically, come
Mhm.
in through afferent arterioles and we leave through efferent arterioles,
So
right?
like that afferent versus efferent, right? Like the
Hmm.
A for coming in, E for leaving off. I have actually a saying that I used to remember the E for leaving, but not appropriate for a podcast, so I'm not gonna share it. But maybe you can look it up at another time. But
You can do E for exit if you wanted to.
you could say E for exit. That's not what I use, but you could say that. You could say that. You could definitely say that,
All right, I'm gonna have to Google that one later, Mike.
100%. We'll talk about it after the podcast. But you're right. A coming in, E exiting or leaving, 100%.
Yes. And between that, we go through the glomerular capillaries, right? Now, this is a very important stage, right? Because ultimately we talked about Bowman's capsule as sort of a cup that's going around this capillary. Blood itself is not leaving. In fact, a lot of the really large components of our blood, things like cells and large proteins, will not be filtered in the
Mhm.
kidneys, right? Or at least they shouldn't be. And if they are, it's actually a sign that something's wrong. What we
Mhm.
see is water and solutes for the most part leaving the bloodstream at this point. And this is a big application to fluids,
Mhm.
right? Because you have all of the pressure, all that
Oh,
hydrostatic pressure.
oh, hydrostatic pressure. We're
I
back.
know it's coming up again, right?
Right.
All the pressure associated with blood pushing this, blood forward in that capillary, it's very significant,
Mhm.
right? And ultimately, we talk about forces that push blood and especially the fluid in the blood, and the solutes that are dissolved in that fluid, push it out of
Mhm.
that capillary. That's the hydrostatic pressure. There is also a sort of a sucking pressure. If
Mhm.
our bloodstream is a lot more concentrated than our surroundings, right? We want solutes to come in. In this case, in the glomerular capillaries, that hydrostatic pressure is much higher, right? The pushing pressure is much higher than the sucking pressure, which
Mhm.
means that when that blood flows through the afferent arteriole into the glomerular capillary, we have fluid and solutes that are in it leaving, right? It's
Mhm.
being pushed out of the bloodstream into the area around it, which, as we so nicely described, is held on to, right? It's surrounded by Bowman's capsule. So
Mhm.
we have fluid and solutes leaving that
Mhm.
glomerular capillary, or just the glomerulus,
Mhm.
and all of that fluid and those solutes are caught by Bowman's capsule and sent on through to the rest of the nephron.
Right, right. There was something actually there. I kind of had a question for you. You said that there was this hydrostatic pressure really pushing in, but then you said there was this suction force. What's the name of that suction force that students might see on the exam?
Yeah, so it's basically this idea of osmotic pressure.
Mm,
You may sometimes see it as oncotic pressure, which is just more specific to the bloodstream, but osmotic pressure is that sucking pressure, right? Where basically the water surrounding your capillary bed, right,
mhm,
is wanting to come in, right? You have
mhm,
fluid wanting to enter the capillary, enter the
mhm,
bloodstream because your blood is so much more concentrated than the area around it.
mhm,
So we have two different pressures that are
mhm. Kind
being
of opposing
created. And
thing, right?
yeah, the net movement of fluid is going to depend on which one of those pressures is greater. So in
Mhm,
this case, the pushing pressure of pushing fluid out of the bloodstream into essentially Bowman's capsule, which is
mhm.
surrounding it, is greater than that sucking pressure or that pulling pressure where fluid wants to move into the bloodstream. So
Right, right.
net movement of fluid out,
Mhm,
right? And this is ultimately filtration. When
right.
you are talking to a patient that's, let's say, in experiencing chronic kidney disease, they'll probably tell you their GFR. That's glomerular filtration rate.
Mhm,
That's how much fluid is being filtered in the glomerulus.
right.
So we talk about kidney disease in different stages. You don't need to know this for the exam, but it's all based on how well blood is being filtered at the glomerulus.
Right, right.
So
And
super
it's
cool.
like the sieve, yeah. And I love this idea that like, especially when students hear these terms like osmotic pressure or hydrostatic pressure, we're like, how do these two fit? There's these pressures, like which one's which? Like I like thinking about it like, yeah, as this fighting force, where hydrostatic pressure is like that blood
Mhm.
pressure pushing things into the glomerulus or out of the glomerulus into the Bowman's capsule. Osmotic pressure is trying to suck it back into the blood. And it's really these two opposing forces that, but generally the hydrostatic pressure is generally greater. So we have net leaving the blood, which is very, very cool. I like thinking about like the glomerulus kind of like a net, right? Because a
Mhm.
net, right, has like a whole bunch of holes, but the holes aren't specific, right? As long as it's big enough to go through the hole, it's gonna go through the hole, right? And that's why the bigger things, like you were saying before, red blood cells.
If it's small enough to go through the hole, it will.
Oh, sorry, I might have misspoke. Yeah, if
Yes.
it's sorry,
If they're too
I'm
big, you
big,
won't.
like
Yeah.
big enough, like the lack of big. If it to go through the hole, kind of like
The lack
the
of big.
it's if it's the lack of big, it will go through the
I
hole.
think that's called small, Mike.
Never heard of that.
No, no, you're
But if it's
right.
small enough to go through a hole, you're right. Yeah. If it like kind of like a net, if it's small enough, it will pass through. But that's why those bigger portions, like large protein cells, it's not like it's these selective transporters or anything like that. No, it's like legitimately, if you're small enough to go through that hole, you will go through that hole. And so
Hmm.
this is a really important idea to have before we go to the next part of the nephron because you can imagine there's probably a lot of stuff that go through those holes in like into the bones castle that you don't want to go in there, right? There's probably
Hmm.
things that are very critical, things like electrolytes, vitamins, smaller. I don't imagine that many proteins will be going through. That would not be great. But like these smaller portions, like these smaller things that are really necessary are going through that we actually want in the body. Like things like glucose as well.
Hmm.
Like I don't want to lose a
Yeah,
lot of my glucose
glucose.
is a big one. I mean, that's in diabetes, like there's so much glucose you actually see that in the urine. But this idea is important when we go to the next portion of the nephron, which is the proximal convoluted tubule. Again, proximal meaning close to the glomerulus. It's close proximity. And the whole goal of the proximal convoluted tubule, again, it's the first stop of the filtrate. That's that liquid inside the nephron. We call it the filtrate. This is when we're kind of taking back all this stuff. We're like, oops, a lot of that stuff was supposed to go in the nephron or that's going in the nephron. I don't want all that stuff. So this is where we have kind of a bulk flow or a bulk reabsorption of a lot of those components. This is where a lot of water is reabsorbed, a lot of glucose, some amino acids, the electrolytes. These things that we need and we that are not waste products are coming back into the blood. Again, kind of like just like a lot of stuff is just coming back. And here you also not a lot, but we also have some secretion at the proximal convoluted tubule. Because, like we mentioned before when we were taking our terms, there's a difference between filtration and secretion. Again, a lot of stuff enters through the like filtration, the glomerulus. But here is where we also secrete some of the waste products that wasn't filtered in the glomerulus into the nephron through this mechanism as well. But the big idea in the proximal convoluted tubule is that we're taking back a lot of the stuff that we did not mean to enter into the nephron and kind of
Yeah.
secreting a little bit of other waste products that wasn't filtered there. So again, when thinking about the proximal convoluted tubule, very not, I wouldn't say it's as kind of like fine tuning as selective or as some of the other things that we're about to talk about. And here, the proximal convoluted tubule, there's not many hormone, there's not none that for the MCAT at least that really impact the proximal convoluted tubule. When we talk about control of what's regulated in terms of like what the nephron does, it's generally the other portions of the nephron that
Hmm.
are like really regulated. Proximal is just, let me just take back all this stuff that's not supposed to be here.
Let me just undo that real quick.
Yeah, let me just retcon that.
Yeah, and I feel like it's important to address that a lot of students pull up a picture of the nephron and what is secreted and filtered and reabsorbed and all that. And they see this long list of all the
Mhm,
ions that are filtered and all the molecules that are reabsorbed, and et cetera, right? Like, and it gets really overwhelming. Do I need to memorize everything? And the answer is
mhm.
probably not,
No,
right? I would think of it this way. One, first thing, is this small enough or not big
not
enough
big enough.
to fit through the capillary,
Mhm,
right? And out into Bowman's capsule. If it's a giant protein, a huge, albumin, or if we're talking about red blood cells, white blood cells, things like that, no, not going to be filtered. It's not going to be in our nephron, or at least it shouldn't be, again, unless we have some issues with our
mhm,
kidneys. First question, right? Okay, something small like glucose, right? Or
mhm,
ions or amino acids. Okay, those might be small enough. All right. Then we have to think, basically, second and only other question is this something I probably want to hang on to? Or is
mhm.
this something that I don't want? Is this a
Right.
waste product or is this a nutrient or something that provides a benefit to me? Right? Generally speaking, like you said, we are reabsorbing all the good stuff and we're secreting all the bad stuff, right?
Mhm,
So that's the basics, right?
mhm.
Don't sit there, pull up a diagram and feel like you need to memorize
Memorize
every single
everything.
ion, every
Hmm.
single thing, right?
Hmm.
Especially in the proximal convoluted, like you said, it's bulk flow.
Hmm.
Good stuff in or good stuff back into the body, I should say. Bad
Hmm.
stuff into the filtrate, get rid of it.
Right. Right.
Um, not the most I guess fine-tuned section
Yeah.
of our
Not
kidney, right?
really
It's
no.
pretty general, right?
Hmm.
And I think a general understanding of what's good and bad for the body can get you most of those questions if you have a
I can't.
specific question.
To be honest, I can't think of a single question you wouldn't get, especially like specifically on the
Exactly.
proximal. Like again, this is those kind of conversations are especially for some of the structures down the line in the nephron.
Yeah.
I feel like
Yeah.
whenever I see the proportion of kidney questions, they're either in the glomerulus or they're like some of the other portions, like loop of Henle, distal, collecting duct. So
Yeah.
I feel like proximal doesn't have that many questions because of the lack of specificity, right?
Yeah, and you know what? Now that we're saying that, same with filtration. I feel like
Yeah,
filtration and I feel like now that I'm thinking about it, we just get more specific and regulated as we
as we
move through
go.
the nephron.
Right, right.
The first two stages are really general,
Really
right?
general.
You
You big
filter
enough?
whatever's small
Yeah.
enough to fit through,
I
and
keep
then
on.
you pretty
Yeah.
much take back the good stuff and put more of the bad stuff in,
Mm-hmm.
right? As we move into the loop of Henle,
Mm-hmm.
right, we see a little bit more specificity, right? Specifically, we are dealing with sodium and water. That's the
Mm-hmm.
biggest two.
Mm-hmm.
So keep in mind, we're starting off pretty much on the same plane, right?
Mm-hmm.
The glomerulus and the or the proximal convoluted tubule are kind of right next to each other.
Mm-hmm.
We're now going to dive deep into the nephron, right? Or
Right.
into the kidney, right? We're diving down deeper in what's called the descending loop of Henle. Okay,
Mm-hmm.
descending because it's going down
Down.
deeper, right?
Right.
The idea with the descending limb of the loop of Henle is we're losing water.
Mm-hmm.
We'll talk about this in a second, right? But the kidney gets saltier as you go deeper down into the kidney. So as we dive down, right, what we talked about with osmosis is the surrounding area is a lot more concentrated. Water wants to move,
Mm-hmm.
right? Water is essentially leaving
Mm-hmm.
because the surrounding areas are so salty. This is
Mm-hmm.
totally passive. So water is leaving the descending loop of Henle. And then as we kind of take a U-turn essentially and start heading back up, we're actually now, there's no aquaporins, there's no channels for water on the ascending loop. Now we care about sodium.
Mm-hmm.
Okay. The ascending loop has a thin and a thick portion. We
Mm-hmm.
start off thin, which
Mm-hmm.
makes sense because if you were to look at a diagram, the descending limb is pretty much all thin, right?
Yeah.
Ascending, we go around that little U-turn, we go up a little bit. We're still thin. This thinness represents passive transport,
Mm-hmm.
right? So right around that little U-turn, we start to
Mm-hmm.
passively lose sodium. Again, we're not losing water at this point because we don't have the channels for it. As you continue to go up, right, we're not able to do this passively anymore. This now
Mm-hmm.
becomes active. And as such, we're going to see a thicker ascending limb
Mhm.
where it is active. Because I always like to think about this as just you need a lot more machinery. This is not a
Yeah.
passive process.
That's why it's so thick. I like that.
That's why it's so thick. That's
Right.
how I always thought about it.
Hmm.
Um, but I think with the loop of Henle, what's important to understand is we're mostly thinking of salt and water.
Hmm.
Down, you're losing water.
Hmm.
Up, you're losing salt,
Right.
right?
Right.
And this helps address why this kidney is so salty,
Right.
right? Mike, walk us
So,
through that.
so for sure. Like, and I think it's important when we think about like these different portions of the kidney. You kind of already mentioned it before. Like this inner saltier portion of the kidney is known as the renal medulla. Right,
Hmm.
where we were working before, the glomerulus and the proximal convoluted tubule, that was generally in the renal cortex. So
Cortex.
you see this cortex medulla in a lot of structures, actually. Like the first one that comes to mind is the adrenal cortex, adrenal
Yep.
medulla. But yeah, it's this idea that the cortex is on the outside, the medulla is in the middle, right? And this idea that this medulla in the middle is really salty, and the reason it's so salty is because of that ascending loop of Henle. Well, that's actively, right? It's actively pulling out salt. And it's this active pulling out salt is what creates the salty environment that affects the descending limb. This idea where the ascending limb creates the salty environment that pulls the water out of the descending limb passively is known as the countercurrent multiplier system or the countercurrent system, where it's the idea that we, from the ascending limb, creates that salt gradient that passively impacts that water gradient on the descending limb. So that's the kind of, the MCAT will expect you to know that term, the countercurrent multiplier system, but simply is this idea that the ascending limb creates that salt gradient that's going to impact that descending limb. It's the reason why the medulla is so salty and the cortex doesn't really have that saltiness. Right. And this kind of like, again, now we've like really like at this point, we've really concentrated the urine. Like we've like really concentrated the urine. We've taken out a lot of water, and we've like taken out a lot of the salt. And now this is the portion, now we get back up. Now we've ascended back up to the renal cortex. And now we've entered what's called the distal convoluted tubule. Again, different from the proximal. Proximal was, in terms of the pathway, pretty close to the glomerulus. Now we've gone further away. That's why it's distal. Generally, when we think of distal, it's further away. And the distal convoluted tubule is actually quite different from the proximal convoluted tubule in terms of its sort of intention and control. Here is where we've kind of done like a lot of the bulk flow and kind of really taken a lot of that water and sodium out. But now this is where we fine tune the filtrate. This is where we fine tune the sodium balance and the water balance of the body and the what's actually inside. And this is where you're going to have the action of some hormones. There's one
Mhm.
in particular that we've sort of mentioned previous episode that really has their impact here, and that is aldosterone. Right, that's that aldosterone from the RAAS system from before. And Molly, remind me, what's the impact of the RAAS system and specifically aldosterone?
Yeah, so aldosterone is all about helping regulate blood pressure, right?
Hmm.
We secrete, well, all components of the RAS pathway. We activate the RAS pathway when blood pressure is too low,
Hmm.
right? And the end product of that pathway is aldosterone, which is
Hmm.
going to help us increase water reabsorption,
Right.
but specifically by increasing sodium reabsorption.
Absolutely. Specifically at the distal convoluted tubule, right? It doesn't act on the loop of Henle. It doesn't act on the proximal because, well, there is salt regulation in both those places. Again, this distal convoluted tubule is really where the control happens, really where the fine tuning happens, and this is where the aldosterone impacts. It's
Mhm.
here that we now, especially if we have a high level of aldosterone, start uptaking even more sodium from the filtrate into the blood. But by taking that sodium, what will follow because of osmotic gradients is water as well. More water, increasing blood pressure. And so the key idea here is that distal convoluted tubule, this isn't bulk flow. This isn't just like, oh, we're just taking up all the good stuff. This is where the control happens. This is where regulation happens. As well, not only do we have reabsorption, but we also have some very controlled secretion in the distal convoluted tubule as well. Again, the big idea here, a lot of regulation, very, very specific. And so depending on the environment, depending on what the body needs, we might be reabsorbing sodium, reabsorbing water. We might not be doing as much depending on the body's needs. But then that's what takes us to, now that we've done this fine tuning of our electrolytes, of our sodium, it takes us to kind of the final portion of the nephron.
Yes, which is the
Right?
collecting duct, right? This is our last stop before,
Mhm.
again, we are going to kind of all pool into the ureters and go out right? Exit the body through the urethra.
Mm-hmm.
The collecting duct is really our last chance to grab as much water as, not as much as we can, as
Mm-hmm.
much water as we need. And
Mm-hmm.
that's a very important idea because we
Mm-hmm.
do not grab every single water molecule that we physically can, or
Mm-hmm.
every molecule that's in our urine. We actually need a fair amount of water in our urine to keep all of those solutes that are leaving dissolved, right?
Mm-hmm.
Some of the components of our urine, right, especially nitrogenous wastes, are actually
Mm-hmm.
really, really dangerous
Mm-hmm.
if they are not properly dissolved in water,
Right.
like ammonia becoming ammonium.
Mm-hmm.
So we need water in our urine, but we also want to make sure we don't dehydrate ourselves,
Mm-hmm.
especially if we are already dehydrated. We want to make sure
Mm-hmm.
that we aren't, essentially peeing more than we should. So this collecting duct is a very, very important place for regulation of water balance.
Mm-hmm.
So you had already mentioned, right, that the RAAS pathway and aldosterone can act to increase sodium reabsorption in the distal convoluted tubule, right?
Mm-hmm.
Coming into the collecting duct, we've got aquaporins, right, which
Mm-hmm.
are transport molecules that will allow water to move out passively. It's not active. It's
Mm-hmm.
a passive process. It's what we call facilitated diffusion, basically
Mm-hmm.
just opening a door that water can leave if it wants to.
Sure.
Um, this is a very important process. Again, naturally, with no hormonal input, you'll have some water reabsorbed. Not going to be a ton, but you'll have some. Um, with low blood pressure, let's say, or with, some signal to the body that we need to increase water reabsorption,
Mm-hmm.
collecting duct is going to be a really important piece of this, right? So,
Absolutely.
okay, we reabsorb salt
Mm-hmm.
from our filtrate in the distal convoluted tubule. Water is going to want to flow out, right?
Mm-hmm.
Water likes to follow salt. We see that with diffusion and osmosis, right? Which is essentially diffusion of water.
Mm-hmm.
And that's very important, right, with the RAAS pathway and aldosterone. But with the collecting duct, we also have to be thinking about another hormone called antidiuretic hormone, or ADH, or vasopressin,
Right.
right? This is another hormone that responds to low blood pressure, but this acts in a completely different way,
Mm-hmm.
right? So we see the RAAS pathway active when we're not as worried about our blood osmolarity, which is basically
Mm-hmm.
how much salt we have in our blood,
Right.
right? We know that with the RAAS pathway, we absorb salt and water.
Mm-hmm.
ADH is primarily secreted, right, into
Mm-hmm.
the bloodstream when our blood is too salty.
Too
In that
salty.
case, we don't want any more salt in at that
Mm-hmm.
distal convoluted tubule. All we want is water to
Mm-hmm.
balance out the salt that we already have in our bloodstream. So what ADH is going to do is take some of those excess aquaporins that are not in the membrane, but that are kind of stored in the
Mm-hmm.
collecting duct cells.
Mm-hmm.
And we're going to get extra aquaporins on that membrane so more water can be reabsorbed, right? So that is very, very important. ADH is the most important hormone that's going to act on this collecting duct. And we're most of the time without ADH, we absorb some water, but not a
Mm-hmm.
ton. When ADH signaling is present, we reabsorb a lot of water.
Mm-hmm.
Again, the goal is to take our blood, which currently is too salty, and bring us back to our homeostatic set
I
point.
was waiting for this term this entire. I was like, we have the whole episode, last episode on homeostasis. This is a great place to talk about it. I'm like, this is that
Yes,
homeostatic balance we were before. We just became, hey, remember when we were talking about like MCAT style questions, like what happens when the blood gets too salty? Well, right. Well, we probably want to get it less salty, more watery absorbed. What's going to do that? ADH, right? Absolutely,
exactly.
100%. Right.
Yeah, homeostasis is a huge topic here, and I feel like there are a couple things that we could run through as far as like if you have a Gen Chem passage that's about homeostasis, like
Mm-hmm.
it's very possible you could see questions about these as
Mm-hmm.
applications, or vice versa, right?
Mm-hmm.
If you have a bio passage that's about the kidneys, expect to see biochem and Gen Chem questions about
Sure.
this.
Sure.
Um, so with the kidneys, right, as we talked about, it's all about balance,
Mm-hmm.
right? We're maintaining solute concentration, we're maintaining glucose levels, we're maintaining water balance, we're getting rid of things like nitrogenous waste. Balance is key, which is why
Hmm.
we talk about this right after
Of
equilibrium.
course, of course.
Um, so we talked about water balance. With
Right.
ADH, we talked about aldosterone and kind of
Mhm.
salt/water balance.
Right.
What else might we be regulating
So
or maintaining in equilibrium?
before we move on to water balance, I was like thinking of like a real world example of water balance and
Mm.
actually where water balance actually is not regulated, specifically
Ooh.
here.
Ooh.
And I kind of like thinking about like alcohol consumption. We know when
Mm.
alcohol is consumed, the amount of urine that is outputted drastically increases. Drastically. And
Ah.
so I love kind of relating to this because again, some people, a lot of students have consumed alcohol before in a reasonable amount. And so like, wait a minute, why is it that we now our urine output so much higher? It's because of alcohol's impact on ADH levels. Alcohol
Ah.
actually downregulates the amount of ADH. So if we are downregulating the amount of ADH, are we reabsorbing as much water anymore?
We are not.
We are not. And it's for this reason. Why? Imagine all that urine is just all the water you're not reabsorbing anymore. And that's why you urinate so much more as a result of alcohol consumption. And also why dehydration is a huge risk, when you consume alcohol, because you're not reabsorbing as much from the kidneys.
Wow, what a
Right?
cool thing to add. I love
Right.
that.
I love this one because again, I love whenever there's like a real world example that is like a shared like again like everyone knows like oh you pee more when you urinate more when you have alcohol
Right.
consumption. Relating your MCAT content to that, like you're never gonna forget that anymore. So I love that
Yeah.
and I love like this is a great place where you have now added something exogenous that has messed up your homeostatic balance. Right?
Yes.
Messed up the ways that your bodies like to regulate. So yeah, just thought I'd do that before we talked about kind of the next things that our body can regulate using the kidneys.
I love that.
Right.
Sweet. Yeah, I love getting like real world applications whenever we can. Makes things a lot more fun, right? Especially when you're saying, basically the experience of being hungover
Hmm.
for a large part is because of the dehydration. And the
Right.
dehydration is because of the loss of ADH signaling, right?
Right.
So ultimately, like that's what we're talking about is the reason why if you drink you can get hungover. It's the reason why if you drink you pee more, right?
Hmm.
Um, and the reason why it's very important to also maintain your water
Right.
uh, intake whenever, right?
Sure. Of course.
Whether you're drinking alcohol or not, make
Hmm.
sure you're maintaining your water. Um, and also, I think it's funny, so many people, because, and
Hmm.
we'll talk about this later when we talk about metabolism,
Hmm.
because the body creates water in the process of aerobic respiration. I hear so many students that are like, why do we need to drink
Why do
water
we
then?
need to drink water then?
Why do we
Our
need to
body
drink water?
makes it.
We make water every time we hydrolyze glucose for
Right.
ATP.
Right.
We lose a lot more than we bring in.
Oh, absolutely.
Right,
Absolutely.
in this process, but also if we think retroactively about respiration, we actually breathe out a lot of our water as water vapor.
Hmm.
And when we think about homeostasis and equilibrium, when we talked about body temperature regulation, we also lose a lot of our heat or a lot of our water through evaporative cooling when we
Hmm.
essentially sweat, and
Hmm.
then that water, along with the
Hmm.
heat on the surface of our skin, is being
Hmm.
pulled off of the surface of our skin. It's evaporating, right? We lose a lot of water that way too. So
Right.
between the kidneys and
All
the
those things.
skin and the
Yeah.
respiratory system, we lose a lot more than we take in. Please, you guys, drink your water.
Drink it. That if you take something away from today, drink water because it's important.
Yes, and be intentional.
Be
And love
intentional.
Tetra
Well,
Pods
of
and
course.
drink
I mean,
Fresca.
we don't know about that one, but anyway. But that brings us kind of the next one, since we've talked about water balance. Another really important thing that we have referred to quite a bit already in our conversation, the Nephron, is our salt or sodium and potassium balance, right?
Hmm.
Because our salt balance is also regulated, maybe not so much by ADH, but again, by a very important hormone that we've already discussed, which is aldosterone. Not only does it help with blood pressure regulation, but again, if you are lacking sodium in the blood, we have detectors, chemoreceptors that will detect, oh, do I not have enough sodium in the blood? Oh, guess I need to reuptake more sodium. Right? And this is where the effect of aldosterone is, which aldosterone, by acting on the distal convoluted tubule, is going to increase sodium reabsorption, right? Ultimately increasing water reabsorption as well, but as well in the sodium. But it also has another impact that, again, isn't talked about as much, but again, is something to keep in mind, which is its effect on potassium, right? Because again, sodium and potassium are really related, which we know in our sodium potassium channels. Because if we're uptaking more sodium, we're also secreting more potassium because sodium and potassium with these sodium potassium channels go in opposite directions. So we can regulate both sodium and potassium levels through the impact of aldosterone, right? Uptaking more sodium, if I have high aldosterone, I'm uptaking more sodium and I'm secreting more potassium, right? This can be a danger with elevated RAAS levels because if I'm secreting all my potassium, I'm going to have too little potassium, right? And could be
Mm.
really dangerous because potassium is a very important molecule. And so these are the ideas. Again, as soon as you see things like there's some like buzzwords here to know. So as soon as you see things like a lack of potassium or increased sodium, that can maybe be thinking, oh, maybe I have a really active aldosterone, really actively impacting the distal convoluted tubule that's really impacting that regulation. But it also works the other way. If I have too little potassium and too much sodium, maybe we're going to inhibit the amount of aldosterone. So now I'm not going to be secreting so much potassium. And this is a great example, Molly, of what kind of feedback. If this impact is inhibiting my aldosterone.
Well, Mike, that sounds a lot like our negative feedback mechanism,
Oh,
which
absolutely.
pretty much reigns in our body, apart from those very specific exceptions, which
Right.
are positive feedback.
Right, right. And so, yeah,
Yeah.
this is another place where, again, kidney regulating the body, keeping that homeostatic balance, not only of water, but of salt and potassium through these really intentional mechanisms. But again, the kidney is so great because we're not even done with all the things the kidney does. Again, kidney is fundamentally important. So what's the next thing? I mean, we keep on referring to these things in a lot of like the early ones, but what's kind of the next kind of big idea that the kidney regulates?
Yeah, I mean, I feel like it is just so absolutely integral to our regulation of homeostasis,
Mm,
right? Which, by the way, negative feedback, since we brought it up, which is going to be relevant for our last couple applications too. Negative feedback is the idea that you are at equilibrium, you're at
mhm,
your, happy medium, your Goldilocks zone, whatever you want to call it, and
mhm,
then somehow your body is disrupted, right? The
mhm,
equilibrium is disrupted, and homeostasis is going to say that your body wants to restore that, right?
mhm,
It's like Le Chatelier's we talked about as a Gen Chem topic,
mhm,
right? You're at
mhm.
equilibrium, you shift away from equilibrium, your system, which in that
Mhm.
case is just a chemical reaction, not a
Sure.
body,
Sure.
much smaller scale, but you want to shift back, right?
Mhm.
That's negative feedback. Again, you're too cold, cool. Put on extra layers, shiver, vasoconstrict. Now you're warmer. Back to your happy set medium. So that's true of everything we've talked about with water balance, with sodium potassium balance. It's also true of blood pressure regulation. Again,
Mhm.
when we talked about RAS, or I'll talk about ADH separately, I guess. Um, RAS, you're responding to decreased blood pressure, and your job is to increase blood pressure, right?
Right.
And it does this through, again, absorption of sodium, but also the reabsorption of water that follows. That extra
Mhm.
water is going to contribute to extra blood volume, which is going to increase our blood pressure. So the RAS pathway is very, very critical for blood pressure regulation. I
Mhm.
do want to mention that ADH and vasopressin, which are the same,
Mhm.
this is also a pathway that can increase your blood pressure because, again, it's increasing your water reabsorption and
Right.
therefore your blood volume and therefore
Mhm.
your blood pressure.
Mhm.
But again, we're also in that situation concerned about how salty our blood is, right? The
Mhm.
osmotic concentration of our bloodstream. Are we too salty, right?
Mhm.
When our blood pressure is low, you may see both pathways activated. It depends on whatever specific stimulus you have that's prompting activation of these hormones.
Mhm.
And as a hint, if you want to talk more about hormones,
Hormones. Oh,
you
when would
might want
we?
to tune into our next episode when we
Right.
talk about the endocrine system.
Right. A hint, hint. No, judge. Not really a hint because we're just telling you. But yeah, no, because
Yeah.
we've like I
Could
swear,
have
like
done a
over
drum
the
roll, but we
right,
didn't.
no, whatever. But yeah, over the last few episodes, we've been like kind of hinting at hormones. We talked a little about RAS last episode. Yeah, no, with homeostasis, even with the circulatory and respiratory system, there are hormones involved. I
All
mean,
builds.
still RAS. So like, a lot of these hormones, because of their regulation, are so ubiquitous. Thank you. I forgot that word before the episode. Molly reminded me of that word. But they're so ubiquitous because they have such a huge impact on so many systems of the body, and the kidney is not an exception. We've already discussed so many hormones involved, aldosterone, the RAAS system, ADH. I mean, we're going to dive into it way more episode in the next episode. But again, something we really need to consider is that, yeah, when we're talking about these anatomical portions like the kidney, we can't ignore the endocrine system, right? And it's what, again, the MCAT loves to test us, and they love bringing up the kidney and be like, hey, we brought up this hormone. What's the impact on this anatomy? And again, bringing those connections together is huge. So 100%, right? This RAS system, when we talk about the endocrine system, super important. But I mean, we broke down the RAS system a little bit last episode, but why don't we remind people like what does RAS even stand for? Can you remind me what like RAS even means?
Yeah, it's renin, angiotensin, aldosterone system.
Mm-hmm.
And it's weird because there's two angiotensins. There's also an
Mm-hmm.
angiotensinogen.
Mm-hmm.
So
Yep.
you kind of want to go through it step by step. You'd want the nice little flow chart. I
Mm-hmm.
wish we could include a flow
Like
chart in
pictures
here
like on here.
somehow.
You know, if you're listening in and you have the possibility to pull up a flowchart of the RAS system, and this will
Yes.
help. And this will help.
Yes. But if
But
you can't,
uh,
grab your popcorn. Mike, I feel like you should lead us through the RAS system.
oh, stop. Oh, sure. So whenever talking about activating endocrine pathways, the first step is always the signal. What is the signal that activates the pathway? Right? Because we're always responding to things, because that's the whole idea of negative feedback. Something has happened that we need to respond to. For the RAS system, like we talked about before, our blood pressure is too low. That's the problem, right? And how our
Mm.
body detects this, there's kind of like two mechanisms for how the body detects this, right? We have what are called baroreceptors, and these baroreceptors, think of them as like they're a type of mechanoreceptor, so they respond to mechanical movements. And imagine if we have low blood pressure, there's not a lot pressing on those baroreceptors. They're like, oh, I'm not being pushed on very hard. Oh, this is not a good thing, right? Because our blood pressure is so low. So by these like the lack of pushing on these baroreceptors, it activates a pathway. It activates these cells that are right. It's sort of when you think about like the anatomy of the nephron, like the
Hmm.
anatomy of the nephron that we see in pictures is actually a little bit different from reality, where the distal convoluted tubule is actually really close to the glomerulus anatomically, but there's like this cluster of cells in between the two called the juxtaglomerular cells, right? Again, I always have a hard time saying that word juxtaglomerular. I used to never be able to say that word, but juxtaglomerular, I've said it enough times in my life, where they activates these juxtaglomerular cells, and it's these cells that release renin. Renin is the first stop. Renin is what responds to this low blood pressure, because in the body, in the wisdom of the body, my old physiology prof like to say, we need to start a pathway to increase that pressure once again. Okay. And so that brings us to kind of our next step. So, Molly, why don't you pick me off where I left off? Where does renin, what's the next stop for renin? We now have all these juxtaglomerular cells beside, right in between the distal convoluted tubule and the glomerulus, releasing all this renin. What does that renin end up doing?
So I love that you bring this up, right? The juxtam just now I can't say
See,
it. I've
see, I'm not
never had a problem saying this until you said it.
till
The
today.
juxtaglomerular cells,
Hmm.
right, that are actually detecting this drop in pressure and are creating the release of renin, because ultimately renin is kind of the finger that pushes over the first domino,
Hmm.
right? Let's change body systems or change
Hmm.
organs, right? Renin releases from the kidney, and that's going to trigger this pathway. But if we move over to another organ, which is
Hmm.
also very critical for pretty much everything,
So
um,
much.
which would be the liver, which,
Hmm.
by the way, I always tell students, if you get a question that's like, which of the, like, which this function is described in the passage, which organ is responsible?
Liver.
Just put liver. When in doubt, it's probably the liver. The liver
Probably the
does so many
liver.
things.
So much.
One of the liver's many functions is to secrete a zymogen, which is
Ooh,
the
that term.
protein that's
Hmm.
secreted in an inactive form,
Hmm.
right? Called angiotensinogen.
Right.
If you hear ogen, you know
Hmm.
it's a zymogen, which
Hmm.
means this is the inactive or like turned off form.
Hmm.
So angiotensinogen is released by the liver and it is completely inactive until
Until.
we have renin.
Hmm.
Okay, so angiotensinogen is circulating through the bloodstream. It's totally
Vibing.
fine. It's inactive. It's not doing anything. As soon as we detect we have low blood pressure and the kidneys juxtaglomerular
Ah,
cells
I,
release renin,
Mm,
angiotensinogen is
mhm.
cleaved into angiotensin 1.
One. Yes.
Okay.
Mhm.
So now we have renin, we have angiotensinogen, and now we
Mhm.
have angiotensin 1.
One. Mhm.
Now we're
Right.
on to the next step of this domino pathway.
Right. Right.
What does angiotensin 1 do?
Right. And so now angiotensin 1 is kind of, again, there's a reason that we number it because we're like, we know we're not done yet. And this is kind of what brings us to this kind of next organ that you wouldn't generally think is like involved, but we've talked about it already. And this is where the lungs come in. Again, normally we think about like, I remember when I first learned this, I was like, this is so random. Like the lungs are like, I'm thinking about breathing, I'm thinking about pH regulation, but it's also involved in blood pressure. What? Well, the lungs produce a very important enzyme known as angiotensin converting enzyme or ACE. And so,
Oh.
oh, wait a minute, that might sound a little bit
Hmm.
familiar. So the lungs produce this enzyme ACE that, okay, it's being produced. But once this angiotensin 1 is present, now ACE has something to work on. ACE, again, based on the name because it's a converting enzyme, converts angiotensin 1 into angiotensin 2. Right? That's the whole idea.
Hmm.
Because again, this is the next step of the domino effect, right? Where now we have this converting enzyme converting angiotensin 1 to like this really potent angiotensin 2. And
Yes.
but this is where I like to kind of stop because we've talked about something before and something that a lot of people have heard of, and we even discussed it last episode a bit, which are ACE inhibitors. Right.
Hmm.
Again, recall the whole idea of this RAAS system was to increase the blood pressure, right? And so we prescribe things like ACE inhibitors. Again, we are now going to inhibit this step going from angiotensin 1 to angiotensin 2, cutting off this pathway. So is RAS going to be able to do its impact?
No.
Not at all.
Angiotensin 2 is really the powerhouse of this pathway,
Right.
right? Like
Right.
everything is leading to this
Hmm.
molecule,
Right.
right? Angiotensinogen, like we talked about, completely inactive. Angiotensin 1
Hmm.
is not super active. I
Doesn't
mean,
really
it's
do
now
much.
in a form that it can become activated, but it's kind of this middle man of
Like,
just like, so
I'm just
are we doing
vibing.
this or
Are
not?
we,
Right? If
are
you
we
don't have ACE, it's not doing anything special,
right, right.
right? Angiotensin 1 is like a placeholder, right?
Mhm.
Angiotensin 2, as soon
Yes.
as it's made by angiotensin converting enzyme or
Hmm.
ACE in the lungs,
Hmm.
we now have increased blood pressure. And we really see this in two different ways,
Hmm.
right? The first way is the way that we've talked about, right?
Right.
Angiotensin 2 is going to act on the adrenal cortex to produce aldosterone, which,
Hmm.
by the way, is a steroid.
Hmm.
Sterone is a steroid. So this is
Uh-huh.
from the cortex.
Hmm.
We talked about cortex and medulla, so I figured I'd
Right
bring it in.
before. Yeah.
Medulla, adrenal medulla on the inside is going to produce amino acid derived hormones,
Hmm.
epinephrine, dopamine,
Yeah.
norepinephrine.
Yeah. But we'll
Um,
dive into more of that next episode. That's
More of
like,
that
yeah, yeah,
later,
yeah,
yes.
yeah, yeah.
But angiotensin 2 is going to stimulate aldosterone release from the adrenal cortex, which then, as we know, is going to go increase sodium and water reabsorption in the nephron.
Hmm.
Angiotensin 2, though, also has its own function. It can act directly. And to figure out how I would think of the name,
Hmm.
angio is talking about blood vessels.
Hmm.
Tensin is to tense or
Right,
constrict.
right.
So angiotensin 2, yes, activates RAS, but it also directly is going to create vasoconstriction,
Hmm.
right? And we talk about in blood pressure regulation, if we vasoconstrict, we are increasing our blood pressure. We're essentially increasing resistance to
Hmm.
flow. Um, so this can also increase blood pressure. Angiotensin 2, the reason why we take ACE inhibitors is because this angiotensin molecule, or angiotensin 2 specifically, has its direct function, which can be very quick, and it also has a broader function with water balance and salt balance that can change kidney action, right? So RAS as a whole is one giant negative feedback loop. Keep in
Hmm.
mind the stimulus for renin secretion and the ultimate, finger that pushed over our dominoes was low blood pressure. We now have this domino effect
Hmm.
leading towards angiotensin 2, which can directly create vasoconstriction and increase blood pressure. It can also increase water and sodium reabsorption, which will also increase blood pressure.
Right. I think
Blood
this
pressure is too
pathway,
low, bring it
yeah,
up.
it'll bring that up, and then it'll once that blood pressure is higher, hopefully inactivates it, When it doesn't, that's usually a
Mhm.
bad thing. But I love going through this pathway. I love how many organ systems this pathway hits. Like,
Yeah.
first we talk about kidneys, then we're in the liver, then we're in the lungs, then we're in the adrenal gland. Like, it's like it hits on everything. And that's why,
Yeah.
again, I love things like the kidneys because it brings so many things together,
Yes.
right? Which is, again, we can't forget about all those things when we're like doing passages, right? How these buzzwords, when we hear like the RAAS system, shouldn't just be blood pressure. It should activate like
Mhm.
it's a whole pathway with a number of organs involved. And a passage could say something along the lines of, oh, hey, there's an inhibited ability of the lungs to produce ACE. What could be the impact now? Because again, now that we understand the system, that again, this is a multi-organ system that a lot of these different things can have an effect. And that's the kind of context we should be ready for in passages that, okay, it's not just going to be about blood pressure, it could be about all sorts of things, right? Because of all the connections, which I think is super, 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 super cool. We love that.
We
Mhm.
totally do. And it even also connects to acids and bases. We
Right.
talked about the lungs with ACE, but also keep in mind the lungs are very important with the bicarbonate buffer system,
Right.
right? We can change our breathing rate to change how much carbon dioxide we exhale, which
Hmm.
ultimately can change how much acid or protons are in our blood through that bicarbonate buffer system, which we talked about last episode.
Hmm.
The kidneys can also help us with this. We
Hmm.
can change the amount of protons that we are secreting into the
Hmm.
bloodstream to help us respond to more long-term periods of acidosis or when we have too much acid in our blood, right?
Hmm.
So where do you think this would happen based on what we talked about? Where do you think that more fine-tuned regulation of acid-base chemistry would happen in the nephron?
So when I think about like fine tuning, like when I think about fine tuning, immediately I think distal convoluted tubule. Like I'm thinking fine tuning, like whenever we're adjusting to homeostatic places, distal, right?
Yeah.
Because proximal is very bulk, loop of Henle, that's just salt and water. Collecting duct was all
Mm,
about water. The only place that's really left is the distal convoluted tubule.
yeah.
So this is where that fine tuning of like proton, like how are we excreting? Or sorry, not excreting. I mean, it could be excreting, but reabsorbing and secreting protons. Because again, not only can we respond to acidosis, but also alkalosis as well.
Mhm.
And so this is the idea that not only can we respond to pH irregularities by the lungs, we can also have a nephron response to
Yeah.
the acids and bases, which is great because again, like these are the sorts of things that kind of connect. Once again, collect the lungs to the kidneys, which I think is super
Mhm.
important. And again, really speaks to that homeostatic role that kidneys have. Again, we've just talked about four different homeostatic regulation roles that the kidneys have on water balance, salt balance, blood pressure balance, pH balance. It's all about balance with the kidneys, which I think is always such a cool thing to kind of remember and realize just how important these things are.
Yes.
Yeah.
Yeah. And I feel like we really have been working towards this for all of our previous episodes. We even
Right?
saw blood pressure regulation, yes,
Hmm.
but also the impacts of blood pressure in filtration, right?
Hmm.
Every single topic that we've talked about so far in our content-based episodes of our podcast have been addressed here. And I love that. And again, that is our goal, is to show all of the different connections because our body is not a organized textbook with chapters for each standalone organ system, right? Every organ system is cooperating, right? This is teamwork at its
Hmm.
finest, right?
Right.
Every organ system is cooperating to keep the organism alive,
Hmm.
right? So they are so connected, and I think the kidneys give us a really great opportunity to demonstrate that.
Hmm.
Um, so again, we could talk about some specific buzzwords that, like, if you see them, you should be thinking kidneys, but really, there are a lot of them,
There's
right?
a
And
ton.
if we talked about pH at all, right?
Mhm.
That's kidneys. If we talked about bicarbonate or H plus, that's also the kidneys. If we
The
talked
kidneys.
about blood pressure, if we talked about any of the components of the RAAS system, if we talked about ADH vasopressin, if we talked about the adrenal cortex, if we talked about the posterior pituitary, if
Oh
we
my
talked about
goodness.
aquaporins, if we
Ah.
talked about any of the physical
Mm.
markers of the nephron, the collecting duct, the distal convoluted tubule, the loops of Henle. If we talked about acid versus or active versus passive transport,
Right.
oh my goodness,
So many
right?
options. So many options.
I'm going to stop overwhelming you with options, but
I'm dead. I'm like, oh my
there are a
goodness, let me
million.
let me drink it. But again, I think you just such a great important point, which is again why it's important to study these with this context in mind. Because when we are reading these MemCat passages, they're gonna give us terms that should cue our mind to this thing. Like
Yes.
if you see any of those buzzwords, we shouldn't be surprised when we see a kidney question, right?
Yeah.
Because we should already be prepared, already sort of primed. Some psych so we're already primed to prepare for those questions. Because a common question I hear all the time is, how was I supposed to know to think this way? Like I get the solution, but how was I supposed to know I was supposed to think of kidneys, for example? Well, in the
Hmm.
passage, they told us about, pH regulation and blood pressure regulation. While they may not have said the word kidney, we're supposed by looking at the passage, we're primed. And that's why paying attention to these terms and how many things these organs are involved with is really key when answering our questions and going through these passages.
Yes.
Yeah.
And I do want to throw in there, this kind of harks back to our episodes before we started this content-based series, right, where we talked all about strategy. I do also want to mention that learning content helps you a lot to develop that like sort of sixth sense when reading a passage,
Mm.
but it's also very important to do a detailed review. And in
Right.
my experience, the
Mhm.
detailed review is really where you learn how to pick out what's important and
Sure.
how you can make those connections. If you can learn content and from the beginning, you're perfect at identifying buzzwords and
Oh,
identifying connections, more power to
good.
you.
Good on
I
you. I
will
was not
I will be
that.
cheering you on. But for those of us who
Mhm.
want to kind of help strengthen that and don't want to spend a million years with our nose in a textbook
Sure.
or with headphones in your ears listening to podcasts,
Uh-huh.
which I hope
But
you don't, dread.
yeah, I mean, I thanks for
Um,
sticking around to the end.
Definitely, yeah, that's true. Definitely check out our earlier episodes on review because
Mhm.
it's a great it's a great way to kind of build that sixth sense of like, how was I supposed to know that this topic was going to remind me of the kidneys, right? Go back through the passage, see, was there anything even tangentially related to
Mhm.
the kidneys? What if you had to point to some clue in the passage, why were they talking about kidneys? That
Mhm.
exercise is great for helping you build that kind of sixth sense of like, while I'm reading the passage, oh, they talked about bicarbonate buffer. I should be thinking about blood or acid base regulation. I should be thinking of respiratory system, and I should be thinking of kidneys.
And Le
That stuff can be
Chatelier, and
built.
because I love
And Le
Adam Grant.
Chatelier's. Yeah. Depending on the section that we're in.
Right.
Um, but again, we've talked about so many key things here.
Mhm.
And again, we've really been building to this material with so many of our other content-based episodes. But again, yes, you could see discrete, kind of just standalone content questions on kidneys. You can get applications to other material, right, that we talked about. But also, just to prepare you guys, and again, practice is really, really key here. You could also see these in like database passages, right?
Mhm.
The MCAT loves to do that, right?
Mhm.
You could see questions that are asking you to interpret data relating to kidneys. You might see, different urine osmolarity levels. You may see, blood pressure changes represented visually. Different components of the RAAS pathway, for example. It could be mutations in important enzymes or important proteins, like an aquaporin or some sort of transporter. Um, Lots. It also could be questions about hormones, right? So get lots of practice with this. It
Mhm.
is a very high yield concept in and of itself. It's even more high yield with all the applications, and it's even more high yield because of the way that it's tested. It will
Absolutely.
not always be straightforward.
Right. You
So,
can't anticipate the sort of questions they'll ask about kidneys, but a great place to do that practice, again, on our website, if you want really targeted practice, our question bank,
mhm,
I can't recommend them enough. Like honestly, like
yeah,
I don't think enough people know about the question bank. I know we've probably mentioned it like 18 times, but it's just
which is
this
free, by the way.
which is free.
It's
I was
free.
just it's like a totally free resource that if you are looking for you're like Mike and Molly just keep on saying practice, 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 review, review, review. Where am I supposed to do the passages for these things? Well, if you go on the website, we have a completely free question bank with over 6,000 questions, and you can actually select to like work on specific topic areas. If you're like, wow, I need to work on my homeostasis and equilibrium, there's a button where you can click where you just have passages on homeostasis and equilibrium. So if you're like looking for that review, that application of a lot of the stuff that we're talking about here, highly recommend to get that practice in and get that really intentional review. And I can't hype enough our like previous episode on science review. Actually, I've spoken to so many students that were like, wow, like I was reviewing backwards before I review that, before I
Mm.
watched that podcast episode, which we talk about. So highly recommend watching that. It makes the value that you extract from the passages that you do so much, like so much more. You actually get what you need from those passages.
Yes.
Yeah.
And in case anyone is like, oh, 6,000 free questions on, topics like homeostasis and equilibrium, I want that. If you go to our website, on the left-hand side, you'll see question bank,
Mhm.
right? From there, you'll have a couple different options. If you want to do just discrete questions, so just multiple choice, no passage, fundamental discrete,
Mhm.
right? It's going to be where you'll find it. You'll see subjects pop up. You could select if you want to do physics or biochem or bio or psych or soc or whatever. There's also fundamental passages. Those are all meant to be topic specific. We have AMC style where you could do mixed biochem set, for example. But if you want to get practice with this material specifically, you want the fundamental discretes and passages so you can
Mhm.
hone in on one topic area.
Mhm.
And if you are either later in your prep or if you are primarily working with AMC materials, another plug would be our AMC Chrome extension videos.
Oh my goodness.
Very,
Yeah.
very affordable.
Mhm.
I think as of the time this was recorded, it's $29.99 per month.
Per month. Yeah.
Or if you do 6 months, I think it's $19.99,
I have to look
which
back at
is
the pricing.
amazing.
Yeah.
But you get access to all of the video breakdowns for the AMC
Yeah.
materials,
Oh,
including videos Mike and I did.
you'll
Um,
see us there, which is vibes, which is so
yeah,
great.
which is fun.
I was just in a class last night. Actually, I had like 200 people in this class, and I'd asked about the Chrome extension. I had so many people sharing their stories about how the Chrome, like the videos are such a game changer because we
Yeah,
know how bad like those like
video
genuinely
or
bad like
the
the
solutions
AMC
are. Yeah,
solutions are. So not only do you have the written Jack West solutions, you actually have a professional, like one of us or one of the another amazing instructors at JW actually walking you through the problem. It's such a game changer. So highly
yeah,
recommend
for real.
checking that out because I think, yeah, 100%. But also what you should check out is our next episode because we're going to be
Yes.
breaking down one of the, again, if kidneys was important for bringing things together, oh my goodness, is the endocrine system going to shock you? Like knock your pants off. Because the endocrine system is
Keep
we've
your
already
pants on, actually.
keep your pants on, please. But it's gonna be it's gonna shock you because of how kind of integrated the system is, right? If like homeostasis is gonna be a huge idea when thinking about the endocrine system. There's negative feedback, some positive feedback as well, but mostly negative feedback mechanisms responding to changes in the body. That's the whole idea of the endocrine system. We're gonna be breaking down cortisol, insulin, thyroid stimulating hormone, the differences between releasing hormones versus stimulating hormones. Like when you see releasing hormone, what should that tell you? The different connections between these endocrine organs, right? Where are the endocrine organs, their different functions? We're going to be breaking that all out down next episode.
I can't wait. That's going to be
Yeah.
fun. That's going
Yeah.
to be a big episode. Make sure
Right.
you tune in.
Right.
And if you haven't yet heard our previous episodes, either on strategy, which I think we've been doing since like late January or February of
Hmm.
this year,
Hmm.
go check those out. But also, definitely, if anything, retroactively, go back
Hmm.
and check out our other content-based episodes. If you
Hmm.
liked this one, there's a lot of value that we shared in the past couple that really help us understand and conceptualize the stuff that we talked about today.
Yeah.
So be sure to tune in next episode for our discussion of endocrine system. Thank you guys so much for joining us, taking time out of your busy schedules.
Hmm.
And we will see you in the next one.
See
Happy
you later.
studying, everyone.
Happy studying. Bye now.
Bye.